This is Computer Science 455, Software Engineering, continuing our discussion from last time. Today is the 20th of May, Wednesday. So let me remind you first about deadlines. I'm still waiting for the uh, iBox SRS to be approved. We have a maybe it's good to know that the client is requesting some features to be included in prototype 2. So the iBox team is currently negotiating with the client with regards to that. So that's kind of a real world situation where the client requests for different features during the iteration. Um, I'd like to report all SPMPs have been approved and you are actually following your schedule as approved in your document called SPMP. The software architecture and design is currently being reviewed, and I see some deficiencies in the software architecture and design. I need to see the derivation of the pseudocode functions from the low-level design class diagrams and the derivation of the low-level design from the high-level design. I need to see the trace of how you arrive at the low-level design based on high-level design. So there should be there should be um, no gap in the continuity of deriving um, high-level design from your deployment diagram or from some abstract root of your software project, and then from high-level design to low-level design, and then finally from low-level design to pseudocode. And let me show you, remind you about that. If you remember in our previous lectures, we began, ideally, if you like, you can begin from the deployment diagram. The deployment diagram contains the um, uh, components, software components residing on the hardware, and then from there we um, uh, decompose the selected component into its subcomponents. We call that hierarchical decomposition, or the well-known divide and conquer um, strategy that we use in solving complex problems. So from here, we will decompose again B.1 and B.2 into its components. And here, at this level, in this example, B.1 was decomposed into classes. But if uh, the definition of B.1 is still very complex, you can still decompose it into components, and until you arrive at a point where you can determine the classes that will perform the function of that module. So from here, you will have the class diagram B.1.1.2. You'll be able to write the class definition consisting of variables, member variables, and member functions or methods. And then you select which important functions you want to define further. And in this example, you have F2 and FK, and they are expanded into its pseudocode representation. So it's not the target programming language, but a pseudocode that is easy to understand and trace if there is any problem. So this is what I would like to see in your um, software architecture and design, from high level definition in terms of components, breaking it down to its decomposition in class diagram, and then finally the uh, definition of the class in terms of pseudocode. Okay. Now this is ideal if you are um, if you are uh, um, starting from scratch. You are um, you are the first team to actually undertake the project, so everything is fresh and new. Okay, so this is the regular way of deriving the software architecture and design if you are starting your project. Now, what if you are inheriting a project? You are continuing the project. Um, it could be more work because you have to continue where the previous team left off. So I lectured to you before um, reverse engineering. Okay? So if you remember, reverse engineering is a technique where um, you start from the lowest level of the um, decomposition, which is the class, and using the principle of cohesion, you compose those uh, class diagrams into packages. In this example here, I arrive after identifying all the classes that are used in the software. I organize them into packages. So a package here represents a group of classes that have a strong cohesion. Strong cohesion means a strong relation to what the overall function of this set of classes. So in this example, after I identify all the classes, I group them into packages. And how I group them is based on cohesion. So say for example, I determine 10 packages, groupings of all the classes, and I determine the interrelationship between these packages with each other. So this package here is communicating with this package on the left. So the unidirectional arrow determines uh, the direction of communication, and so on and so forth. So you do that, and then afterwards, I said you group the packages into um, um, groups of packages, again applying the principle of cohesion. If the packages have strong cohesion, then group them in a particular group. Another one is right here. These three packages could be grouped into three, and probably the reason you group them into this you group these three packages is because you recognize this is um, a architectural style called three tier. You can do that, three tier um, architecture, and this package here is by itself, and the last four is one big group, okay, with the unidirectional arrow showing the communication between those packages. Then the next step is to replace those unidirectional arrows into ball and socket. Now remember, a ball means I provide service, and a socket means I need service. And from A to B, the relationship of the communication is A provides service and B needs service. But B also provides service to C. And so the communication between B and C, uh, C is a socket and ball, and B is a ball. So we now tackle the last group of four packages with those unidirectional arrows. We replace the arrows with ball and socket with the same definition. And once you did that, now you group all those um, four packages into one component, B. So now the um, uh, the 10 packages that you have started with is now grouped into four components. So that constitute high-level design. Okay? So I need to see the trace from high-level design to low-level design to detailed design, and vice versa. If you are reverse engineering, you are starting from low-level design, which is class, to high-level design, the other way, the other direction. So here you have um, a different direction of, um, of composition or decomposition. Okay, so I need to see that. It's a trace from high-level design to detailed design. For reverse engineering, a trace from low-level design to high-level design. Okay? It cannot be a gap where I see immediately the class diagram without the high-level level design diagram. There must be a trace from one point to another. Okay? All right. So the delivery and QA testing of the first iteration of prototype number one, you have this whole week to do that, 18th up to the 24th of May. Okay? So, um, let me show you the test report. So far, the QA teams are putting together a test report that they will use to test uh, your software. Okay. Okay. So uh, this is troublesome. I always lose the cursor. Okay, let me go to the end and begin all over again right here. Okay, let me show you the um, the current test report that the QA teams have come up with. Okay. So this is still preliminary, and they are still um, consulting with me about uh, the best way to do it. All right. So you have uh, the uh, the report where it says the software title is here, the names of the PM and APM and the software engineers, and they have the test cases that they will try over here for prototype 1. And I recommended that we remove prototype 2 section since we are not testing prototype 2 yet. So they are um, choosing test cases to go over here. The next chapter is testing. So that's going to give you some recommendation on good test, how to select good test cases. But we will talk about it now so you have an idea about test cases. They will test your non-functional requirements. So in addition to the functional requirements, they will also test non-functional like performance, and we measure performances within 2 to 3 seconds. The cursor should be back for the next command from the user. Usability, they will uh, check the sequence of user interface to get to the information that they need. Is it confusing or is it straightforward? Maintainability is a feature where um, uh, there are two big platforms of mobile app today, which is iOS and Android. So, is it prepared to be ported to another platform in the future? And security, some of the uh, projects we have concerns about security. Okay, so they will uh, try to breach security and see if they can access the data uh, unauthorized access of the data. Okay, and did the team perform verification and validation? And this means they want to see evidence of unit testing, integration testing, um, system testing, and regression testing if you have done those. Okay, so all you need is create or show the QA test cases that you have used in doing those testing. Okay, that would be sufficient for the QA team to say, yes, you did it. Now, did you follow coding standard? So they will look at your source code and see if you are compliant with the standard coding that they have specified for Java or Objective-C. Okay, they gave you references on how does that format look like. Uh, did the team uh, submit software metrics? There are two software metrics that we ask you to collect, and that is the productivity of the team in terms of total lines of code produced divided by the time that it took you for design, the time that it took you for coding, and the time that it took you to fix um, errors as well. So debugging. So all those times are put together as the denominator um, to get your productivity. Okay, we will exclude the time spent in the SRS and the time spent for SPMP. Okay, so the total time include the design, coding, debugging. Okay, that's your productivity. Um, did the uh, did the team submit all software artifacts at the repo? Uh, so they will check whether you have a complete um, software artifact stored in your repo. So they will check whether you have the SRS, the SPMP, the SAD document, the source code. Okay, so they will check that, and then of course what I said before, standard code compliance is written here. So those are the items they will review, and you should pass all of them. The functional requirements, all of the all of the test cases should be marked passed. The non-functional test cases should all be passed, and all the supporting um, activities for a good software process is um, will be logged into the test report. Okay, so that's what they're going to do, and be prepared to help the QA team um, perform their testing. Okay, all right. Next is the uh, uh, I like to introduce testing with the Boeing 737 disaster. Okay. Um, okay. So here is a news article. Although this accident um, happened um, last year, uh, the um, the um, disaster happened on the Boeing 737 Max. Okay, so what has been done now? Okay, so there were fixes that were done, but you know what is happening in in that disaster. The Boeing 737 Max jet was fitted with a larger and more efficient engine, and but they have to change the design. Um, I believe the engine has to be moved forward up in the body of the airplane, but it tends to because of the increase in power during takeoff, um, the plane keeps going up, and as you know, in the uh, flying of an airplane, it is possible for the airplane to stall because of uh, too much altitude going past at very fast speed. It could stall. So the system, the software that watch that uh, is called the MCAS, Maneuvering Characteristics Augmentation System, and this is the one that watches if the airplane is going to stall by measuring what we call angle of attack of the airplane or position in the sky. It will force the nose of the airplane um, to level down, so to prevent a stall. So the nose was kept down to avoid that um, uh, uh, the case of stalling. Okay, and in the first two crashes, uh, the nose um, went down 20 times. And the pilot tried to uh, uh, mitigate this by pulling the nose up again. But what happened? MCAS keeps on pulling the nose down, and when that happens, there is no control uh, left in the pilot couldn't control the airplane. The airplane crashed to the ground. Okay, so how they redesign it is the following. They said they have three uh, fixes that they have made to the airplane. Okay, let me. Uh, there it is. These are the three fixes they have made to the software. Okay. So instead of one sensor, MCAS will read from two sensors, and these sensors measure the angle of attack by the aircraft or position in the sky of the airplane. That it doesn't rely on one sensor. The two sensors should agree about the position of the aircraft in the sky. So it will activate only if both sensors agree that the plane's nose is too high. Okay? So there must be two, and this will be an upgrade. Okay? Uh, excuse me. But I think the best fix here that the pilot will be able to override the system. The problem with the previous software, it kept on um, um, it kept the system it kept the airplane going down. The nose is pulled down, and in spite of the efforts of the pilot to pull it up, the airplane kept going down. So it until of course it crashed. So this time pilots will override the system, and this is important because the humans are still better than machines in terms of determining whether there is um, a dangerous situation. Okay, and that is why uh, I don't believe in fully automated automobile. I want to have control and not have the system have full control of the car, because I've seen news where the driver of the car slept all the way. So maybe because of boredom, that the driver fell asleep and therefore trust the system uh, to do everything safely. But I won't trust the system fully. I want to get control manually if needed. Okay. So when they do, MCAS will not automatically reactivate. So when the pilots override the system, the MCAS is fully detached from the system, and which happened in the original system multiple times. So the pilots actually struggled with the controls for I don't know 10 to 15 minutes, and so I could just imagine the pilot trying to save the airplane and their lives by trying to pull the airplane up because the nose keeps diving down. The software keeps pulling the nose down. And here is the number of hours spent with the update. 100. They have flown the airplane 1,800 hours since the new software was installed, and they spent 100,000 hours testing and developing them. Do you know how much 100,000 hours is equivalent to man hours of an engineer? Okay, a software engineer, let's say, works full time, 8 hours a day times 5, that's 40 hours a week. 40 hours times 4 weeks, that's 160 hours per month. So, and there are 12 months in a year. So that would be what? 1,920 uh, hours in a year. Okay. And you divide that by 100,000 divided by 1920. And that's the number of hours or number of um, years one single software engineer will spend to testing. So let us say you have uh, multiple engineers, and that would be something like 12 years if you will be working alone. And of course, if you have 12 engineers, one engineer would have spent 1 year just for testing. Okay, it's a big amount of time for testing. Okay, and of course, uh, the company wants to reassure um, um, the flight attendants about and the pilots uh, that it is safe now to fly in the 737 MAX. Okay, would you fly a 737 MAX? I don't know. I probably have a second thoughts of flying on a 737. But that's the reality of testing. And what happens is that the U.S. Federal Aviation Administration has kind of relaxed their um, their um, regulation on testing with Boeing that uh, they the MCAS problems were the FAA was misled with Boeing, okay, because they kind of became so close, and therefore FAA, even though they heard there is a problem with the software, they still approve the uh, the software. Okay, even though there is some problem with it. Okay, all right. So now, uh, with that in mind, as um, an example for testing, testing is very important, as you know, in software engineering. Without testing, we would not know whether the software will function properly or not in the field. Okay, we only know if it fails. So let me introduce testing in the following definition that we often see when you read article or our book of what is testing. So testing is the process of finding the difference between the expected behavior specified by the system model and the observed behavior of the implemented system. Now remember, uh, the system was conceived as an idea. And when it is developed, the idea is now a concrete software running. So testing is there a difference between what I expect the system to do versus the observed behavior of the implemented system? And in software engineering, like the MCAS problem, um, they expect the behavior to be such a way, but the observed behavior is different. Okay, so it keeps putting the nose down, even though the pilot keeps on pulling it up. That's an unexpected behavior of the MCAS system. Now, unit testing finds differences between specification of an object and its realization as a component. So, unit testing goes to the lowest component of software, lowest level as small as an object or even a program segment. So, unit testing is the you specify the segment of code to produce output, and you unit test it to make sure it actually produces the output you expect. Okay, so unit testing is applied to the lowest component of software to see if it performs the realization of your algorithm. So this is unit testing. If you have the algorithm or pseudocode of the function or of the class, then you unit test it to make sure it behaves what you have specified. Okay, structural testing is much a higher level of of, um, of expectation. You are now talking about system design. Okay, so you have submitted um, high level design, and high level design is the structure of the system itself in high level components like packages and modules. Okay? So when you integrate all of these subsystems together, uh, do they work together as a integrated system? So remember, software is built from small components to bigger components, and so on as you go from bottom to the top level. So Is there a difference of the design, what you expect the design, uh, from the testing of the structure? Okay, so you actually test whether it still fulfills the structure of the design. Okay. Another one is functional testing. So this is a test on the use case model. And this is what the QA team is doing. They're testing your software against your use case. So that is why it's important for the QA team to know your use case diagram. What are the use cases that the software is supposed to fulfill? And, uh, and that's why they perform functional testing. Is it performing the function it was designed to do? Okay? And then performance is the testing difference between non-functional requirements and actual system performance. And performance is always a part of the requirements. If uh, if it is not within the um, uh, performance metric you have specified, like 2 to 3 seconds, then it fails the performance testing. So all of those needs testing to make sure it works. Okay. So let's look at the overview of testing. Okay. Reliability is one of the um, very important uh, property of software. You want the software to be reliable. Okay? So you want the software to be successful in performing its behavior, and it conforms to a specification of each behavior. Because if the software is not reliable, then you cannot expect that the software performs properly at all times. And you want software to perform um, reliably. And there is a measure called software reliability. This is the probability that the software will not cause system failure for a specified time under specified conditions. So if you are maintaining, let us say, the software that controls a ATM um, machine in a bank, and you notice that a lot of customers withdraw money on the ATM during the lunch break, let's say 12 to 1, and the ATM doesn't function or always crash during the 12 to 1 time when people need it the most, because that's when they are free to go to the bank and or ATM machine, then software reliability is compromised. Okay, you want it to um, perform reliably during those specified time. Failure is a deviation of the observed behavior from the specified behavior. So the MCAS software failed because it deviated from the observed behavior from the specified behavior. So it shouldn't um, um, keep the nose going down when it is not supposed to. Okay, and so that's what we want to avoid: failure. Failure is a deviation from the observed behavior. Error means the software hasn't failed yet, but it is in a state that could lead to a failure. So error, uh, we need to avoid that too, because it may lead to uh, a failure condition. And fault, defect, or a bug is a mechanical or algorithmic cause of an error. And this is what we are measuring in terms of um, uh, the quality of your code. We are measuring your uh, you are measuring um, um, uh, your quality of the code that you produce. How many faults does your software has? Okay, per thousand lines of code. Okay, so testing is the systematic attempt to find faults in a planned way in the implemented software. The keyword is systematic. So testing is not done randomly. The testing is systematic. It should be planned. It should be well thought out. And therefore, the choice of test cases is very important, as you will see later on. So it's a systematic attempt. It is not um, a casual process where the QA will just attempt to try some test cases and see that it works. The purpose of the QA team is to find faults in your software in a planned way. So they have to think very carefully about how to test your software to make sure there are no faults or error or failure in your software. So these are the testing objectives that you should have. It is the process of executing a program with the intent of finding an error. Okay? So remember, the intention of the QA team is to crash your program. That's their intention. That's their mission. And so that should be foremost in their mind when they select test cases. They intend to find error. Okay? And a good test case is one that has a high probability of finding an as yet undiscovered error. Remember, error, we can, if we have a good test case, it should be it should have a high probability that you will find an error. Okay, so um, that's why it is called a systematic attempt and a planned way to find faults. Okay? And a successful test is one that uncovers an as yet undiscovered error. And undiscovered error is one you like to avoid. And probably in that MCAS, the undiscovered error was the uh, uh, the sensor is not they rely on a reading of only one sensor when there should be a verification of another sensor to verify the reading of one sensor. So two sensors cannot be wrong at the same time, right? Because if the two gives different readings, then the software should not be activated. So here is the statement I made earlier in the quarter that testing cannot show the absence of defects. It can only show that software defects are present. So if your test case is not good, it doesn't have a probability of discovering an as yet undiscovered error, um, uh, it you can you cannot show that that there are other errors in there. Okay. Now, if you choose a test case that is has a high probability that it will discover an undetected error, it still doesn't show that the software doesn't have defects. It only shows that the probability it will detect an error is high. Therefore, you have a high confidence that the software is good, even though you can't be 100% sure that you don't have any more errors. Okay? So that's the principle that you should have in mind. You must spend a good amount of time in choosing your test cases because you want to have a high probability of discovering an as yet undiscovered error. Okay? All right. Um, continue our discussion of the increasing the reliability of software system, where there are three techniques on how to um, improve the reliability of a software system. And that is the first one is called the fault avoidance. And fault avoidance is a technique where we design the software that we are able to um, build the software for any possible uh, uh, case of having a fault. So, in other words, we have a software that um, a fault cannot occur because we have covered all cases of possible ways that the fault will happen. So this is kind of a strong um, design of the software that you will be able to avoid any kind of fault in the future. And the more you have experienced this, when you are inputting data and you want to make sure that the uh, the user will not input any illegal data. So when the data is inputted, you test for all kinds of uh, uh, tests. Like for instance, did the user input? Let us say you're asked to input a your social security number, and therefore you should check that everything should be numeric, and it's not going to be alphanumeric, that it should be what is that 5 to um, uh, 5 and 2 7 11 exactly 11 digits. What if the user will input only less than 11 digits, or 12 digits or something more? So the more you think about all the possible cases that could happen in the input of your social security number, it's going to grow very large. And so the design of the software becomes large because just to watch for correct input data makes your program very big, and so much more uh, uh, if the fault avoidance is not only on inputting data but other cases as well. So I would say fault avoidance also it may be good, but the software will grow very big as you try to anticipate faults that could happen, and you actually um, build your software to avoid having that kind of error. Okay. uh, the fault detection. So the software is not built as strong as the fault avoidance, but it could detect if a fault is present. So the software is built in such a way that if fault is detected, it shouldn't crash. It should handle the occurrence of an error. So this is where you handle, well, in um, C++, you try to handle all kinds of um, input and and try to detect kind of a detection that the error has occurred. Like for instance, in deadlock. Okay, if you try to do a fault avoidance for deadlock, you will have a lot of a big software to actually avoid having the deadlock. But in fault detection, all you need to do is detect that deadlock has occurred, and you institute ways to avoid, to detect the deadlock. Once the deadlock is has been detected, all you need to do is roll back one of the processes that are in deadlock, and the whole thing will work again. So the fault detection is another way to increase reliability of software system. Detect that deadlock has occurred, then you solve it, not to anticipate all kinds of deadlock that could occur, and try to have a fault avoidance. So the program there is not as huge as the fault avoidance, but it allows the occurrence of a fault, but the software will handle the fault when it happens, and therefore would perform some procedures to actually handle the deadlock. Now, fault tolerance is something that allows the occurrence of the deadlock but won't do anything. Okay. Won't do anything about it. It will just have deadlock, and hopefully the system will not be so um, will not be disrupted so much. But of course, in some system, when deadlock has occurred, you will notice that your program is not advancing. So when that happens, there should be an external intervention to actually remove a process that is involved in the deadlock, and you remove it. So there's an outside intervention to actually remove the deadlock situation. But fault tolerance is a technique where the deadlock is allowed to occur, and if the system is not that critical, let us say for reliability purpose, if it will not cause loss of life, for instance, then it will allow to happen, and when it happens, it just uh, crash, if you will, or like a graceful crashing, and not try to harm the other processes that are going on. So fault tolerance is a technique for handling or for increasing the reliability of the system. Let it occur. Anyway, it doesn't cause too much problem. All we need to do is reboot the system. Just like Microsoft. Microsoft Windows at the early versions of Windows is that it crashed often, and all we have to do is uh, press that reboot button and let it go. Okay, so no harm done. If you're editing a file, you didn't lose any file. You just go back, and hopefully you save it before it crashed. So that will be an inconvenience, but it allows the deadlock to happen, and therefore the system will crash, and all you need to do is reboot. Okay, so that's the end of my lesson today. I introduce you to testing, and next week we will have a full discussion about testing. Okay, um, and good luck to your delivery of iteration one or prototype number one, and good luck on your passing of the QA. Okay, all right. So. Um, uh, be safe and be healthy.